33 trillion kilograms. That's the minimum mass astronomers are attributing to an object currently passing through our solar system. To put that in perspective, it outweighs the Empire State Building by a factor of 40,000. Yet this cosmic heavyweight glides through space, producing active gas jets, while showing virtually no orbital nudge from its own exhaust. It's like watching a freight train powered by birthday candles. This is 3I Atlas, and it's breaking physics in ways that should be impossible. When a comet gets warm, ice sublimates into gas. That gas escapes, creating jets that nudge the comet like tiny thrusters. We've observed this countless times across a century of astronomy. It's basic Newtonian physics, as reliable as gravity itself. Every action produces an equal and opposite reaction. Gas shoots out one direction, the comet gets pushed the other way. Simple, predictable, fundamental. But 3I Atlas refuses to follow the script. Astronomers see clear evidence of outgassing. Water vapor streaming away at hundreds of meters per second. Carbon dioxide creating an extended halo, reaching hundreds of thousands of kilometers from the nucleus. These aren't subtle hints of activity. This object is actively sublimating material into space, precisely the behavior that should create measurable thrust. The expected orbital nudge simply isn't there. 4,022 positional measurements from 227 observatories worldwide paint an impossible picture. The object follows a purely gravitational trajectory, with acceleration limits sitting below 15 millionths of a meter per day squared. That's essentially indistinguishable from an object experiencing zero non-gravitational forces. Yet, the jets keep firing, the gas keeps flowing, and physics keeps getting violated. The only explanation that fits is mass. Extraordinary mass. When you see active gas production, but no measurable rocket effect, something has to give. Either the gas isn't escaping efficiently, which seems unlikely given the visible halo, or the object is massive enough to absorb the recoil without flinching. Current evidence overwhelmingly favors the second option. This creates a paradox that terrifies population statisticians. If 3I Atlas truly weighs tens of billions of tons, with a nucleus spanning 5 kilometers or more, it represents such an extreme outlier that our basic assumptions about interstellar debris might be fundamentally wrong. We should have found dozens or hundreds of smaller objects before discovering such a giant. Planetary systems eject smaller debris more easily. Less massive objects require less energy to accelerate to escape velocity. Detection methods favor moderate-sized visitors. Yet here we are, 3 confirmed interstellar visitors into humanity's search, and the latest is potentially the largest by far. It's like discovering mice by finding elephants first. The order of discovery violates everything population models predict about how matter gets distributed through interstellar space. Either our understanding of cosmic debris populations is completely wrong, our detection methods are more biased than we realized, or we're witnessing something that challenges the very nature of what drifts between the stars. None of these options provide comfort to astronomers who thought they understood how matter moves through the galaxy. Tonight, we examine the silent giant that may be rewriting the rules of interstellar archaeology. The question isn't just what 3I Atlas is. The question is what else we haven't discovered yet. July 1st, 2025. The Atlas Telescope facility in Chile was conducting its routine nightly sky survey, scanning for asteroids and comets that might pose threats to Earth. The automated system had been operating flawlessly for years, cataloguing thousands of solar system objects with mechanical precision. Nothing about that night suggested it would become a turning point in astronomical history. The detection came through at 0300 hours local time. A faint smudge of light moving against the background stars, initially flagged by the automated software as a potential near-Earth object. The preliminary magnitude measurements placed it at around 18, dim enough to have escaped detection by most amateur telescopes, but well within Atlas's capabilities. Within the first hour, the observatory's computers had tracked the object across multiple image frames. The motion was clear, consistent, and unusual. Most asteroids and comets follow predictable paths shaped by billions of years orbiting the Sun. This object's trajectory looked different from the start. By dawn, the data had been transmitted to the Minor Planet Center, the global clearinghouse for observations of asteroids and comets. Astronomers in Cambridge began processing the positional measurements, running preliminary orbital calculations to determine where this object had come from and where it was headed. The first red flag appeared in the velocity data. The object was moving fast, far faster than typical solar system debris at that distance from the Sun. Initial calculations suggested an excess velocity that couldn't be explained by solar gravity alone. Something had accelerated this object to speeds that implied an origin far beyond Neptune's orbit. Within 48 hours, recovery images emerged. Archival photographs taken weeks earlier by other survey telescopes showed the same object in slightly different positions. These additional data points allowed orbital analysts to refine their calculations with increasing precision. The trajectory became clearer, and with it, the unsettling conclusion that had been building since that first detection. This object wasn't gravitationally bound to the Sun. Its orbit wasn't an ellipse, but a hyperbola, the mathematical signature of something passing through our solar system on a one-way journey. The orbital energy was positive, meaning the Sun's gravity would slow it down but never capture it. After swinging through the inner solar system, this visitor would return to interstellar space. By July 4th, the classification was official. The Minor Planet Center designated it C/2025N1, with Atlas in parentheses to credit the Discovery Observatory. But astronomers quickly adopted a simpler name that emphasized its significance: 3I Atlas. The 3I meant third interstellar, a stark reminder that humanity had now confirmed exactly 3 visitors from beyond our solar system in all of recorded history. The professional astronomy community erupted into coordinated action. Observatories across 6 continents began pointing their instruments toward the new arrival. Hubble Space Telescope time was hastily reallocated. The James Webb Space Telescope added the object to its observation queue. Every major facility wanted data on this rare visitor before it disappeared back into the cosmic dark. Nobody yet realized just how strange this visitor would prove to be. The first clue that something was wrong came from the orbital refinement process. As observatories worldwide tracked 3I Atlas through July and August of 2025, astrometrists noticed something peculiar in their residual plots. The difference between where the object actually appeared and where pure gravitational calculations predicted it should be was essentially 0. This shouldn't have been remarkable. After all, gravity governs the motion of objects in space. But for active comets, pure gravity never tells the complete story. Every comet studied in the modern era shows what astronomers call non-gravitational acceleration. When sunlight warms a comet's icy nucleus, frozen material sublimates directly from solid to gas. This gas doesn't just drift away peacefully, it erupts in jets, sometimes violently, carrying momentum away from the nucleus. Newton's third law demands that this escaping gas push back on the comet itself, creating small but measurable forces that alter the orbit over time. These non-gravitational forces have been observed in hundreds of comets. They're as predictable as sunrise. Large comets show smaller accelerations because their greater mass resists the push. Small comets show larger accelerations because the same gas production has more influence on less mass. The relationship is well understood, tested, and reliable. 3I Atlas was clearly producing gas. Spectroscopic observations showed water vapor, carbon dioxide, and other volatiles streaming away from the nucleus at hundreds of meters per second. The extended coma, the hazy envelope surrounding the solid core, stretched hundreds of thousands of kilometers into space. This wasn't subtle outgassing. This was active, vigorous sublimation of the type that should create obvious orbital perturbations. Yet, the acceleration simply wasn't showing up in the data. By September, astronomers had accumulated over 4,000 positional measurements from more than 200 observatories. The precision was extraordinary, with individual measurements accurate to fractions of an arcsecond. String enough of these measurements together over months of observation, and even tiny accelerations become detectable as systematic deviations from gravitational motion. The upper limit on 3I Atlas's non-gravitational acceleration sat below 15 millionths of a meter per day squared. Convert that to more familiar units, and you get roughly 2 billionths of a meter per second squared. That's about 1/10 millionth the acceleration you'd feel in a gently moving elevator. Extraordinarily small, essentially indistinguishable from zero given the measurement uncertainties. But here's what made this result so disturbing. Based on the observed gas production rates and typical comet physics, 3I Atlas should have been showing accelerations at least 10 times larger, possibly 100 times larger. The gas was there, the jets were firing, the momentum was leaving the nucleus. Conservation of momentum is not optional in physics. If gas carries momentum away, the source must recoil, unless that source is so massive that the recoil becomes undetectable. Unless you're trying to move a mountain by throwing pebbles at it. Unless 3I Atlas isn't a typical comet at all, but something far more substantial, masquerading as an ordinary icy visitor. The implications were staggering, and they pointed toward a conclusion that challenged everything astronomers thought they knew about interstellar debris. The thermodynamics problem facing astronomers was elegantly simple and profoundly troubling. Gas was escaping from 3I Atlas at measurable rates. That gas carried measurable momentum, yet the nucleus showed no measurable response to losing that momentum. Somewhere in this chain of observations, something fundamental had to give. The physics of comet outgassing has been understood for decades. When sunlight warms an icy surface, molecules gain enough energy to break free from the solid matrix. Water ice sublimates at predictable rates, depending on temperature and solar distance. Carbon dioxide sublimates even more readily, becoming active at much greater distances from the sun, where water remains frozen solid. As these molecules escape, they don't just evaporate quietly. Subsurface pressure builds until gas erupts through weak points in the nucleus, creating collimated jets that can persist for hours or days. These jets behave like natural rocket engines, and the thrust they produce follows straightforward physics that any engineering student could calculate. For 3I Atlas, spectroscopic measurements provided concrete numbers. The object was losing approximately 150 kilograms of mass per second through outgassing. That might sound modest, roughly the weight of 2 people every second, but momentum adds up. Over days and weeks, this continuous mass loss should produce acceleration that even distant telescopes could measure. The gas velocity measurements came from analyzing spectral line profiles. When molecules emit light, thermal motion and bulk flow combine to broaden the spectral signatures in characteristic ways. For 3I Atlas, these velocities sat around 440 meters per second, typical values for gas escaping from comet nuclei under solar heating. Simple multiplication reveals the momentum problem. 150 kilograms per second moving at 440 meters per second represents 66,000 units of momentum, leaving the nucleus every second. Conservation of momentum is perhaps the most fundamental principle in classical physics. This momentum cannot simply vanish. It must go somewhere. If the nucleus were a typical comet, say 1 kilometer across, with mass measured in billions of tons, this momentum loss would create obvious acceleration. Observations would show the object drifting away from its predicted gravitational path by amounts easily detectable with modern astrometry. Dozens of solar system comets show exactly this behavior, but 3I Atlas absorbed this continuous momentum drain without flinching. The only way to make the physics work was to increase the denominator in the momentum equation. Force equals mass times acceleration, which means acceleration equals force divided by mass. If the force is fixed by observed gas production, and the acceleration is observed to be essentially zero, then mass must be enormous. The calculations pointed toward a nucleus at least 5 kilometers in diameter, with mass exceeding 33 trillion kilograms. This wasn't just large for an interstellar visitor. This was orders of magnitude more massive than any comet humanity had studied in detail. It was a mountain of ice and rock that happened to sublimate like a comet while behaving gravitationally like an asteroid. The thermodynamics were clear. The observations were reliable. The conclusion was unavoidable. 3I Atlas was something unprecedented, and the astronomical community was only beginning to grasp the implications. The calculation itself was straightforward, almost embarrassingly simple for professional astronomers. Take the observed gas production rate, multiply by escape velocity, divide by the upper limit on measured acceleration, and the result gives you minimum mass. Basic physics that any undergraduate could perform. The problem wasn't the math. The problem was believing the answer. 33 trillion kilograms as a lower limit. Not an estimate, not a best guess, but the absolute minimum mass consistent with observations. The actual mass could be higher, possibly much higher, but it couldn't be lower without violating conservation of momentum. To put this in perspective, researchers began comparing 3I Atlas to familiar objects. The Empire State Building weighs roughly 800 million kilograms. 3I Atlas outmasses it by a factor of 40,000. Even that comparison fails to capture the scale. This object contains more mass than some of Earth's smaller mountains. The size estimates followed from assuming typical comet densities around 500 kilograms per cubic meter. These densities come from direct measurements of solar system comets by spacecraft missions. They represent a reasonable baseline for objects composed of ice and rock in roughly equal proportions. Apply this density to 33 trillion kilograms, and you get a sphere at least 5 kilometers in diameter. 5 kilometers. That's larger than the object that killed the dinosaurs 66 million years ago. That's a nucleus rivaling some of the largest comet nuclei ever measured in our solar system. And this behemoth was supposedly ejected from another stellar system, accelerated to interstellar velocities, and sent wandering through the galaxy. The comparison to previous interstellar visitors made the mass estimate even more disturbing. Oumuamua, discovered in 2017, probably measured less than 1 kilometer in its longest dimension and weighed perhaps millions of tons. 2. Borisov, discovered in 2019, had a nucleus roughly 1 kilometer across, containing billions of tons of material. 3. Atlas potentially outmassed both previous visitors by factors of 10 to 1,000. Population statisticians immediately recognized the problem. In every plausible model of planetary system evolution, smaller objects get ejected more easily than larger ones. Less massive debris requires less energy to accelerate to escape velocity. The interstellar medium should be populated primarily by modest-sized objects with rare massive specimens mixed in at very low frequency. Finding the massive specimen third, before adequate sampling of smaller populations, violated statistical expectations so severely that it demanded explanation. Either detection methods were far more biased than anyone realized, or 3I Atlas represented a genuinely anomalous event, or fundamental assumptions about interstellar debris populations needed revision. The calculator hadn't broken. Reality had. Between May 15th and September 23rd of 2025, astronomers compiled one of the most comprehensive tracking campaigns ever mounted for an interstellar visitor. 4,022 individual positional measurements from 227 observatories scattered across 6 continents. This wasn't casual observation. This was precision astrometry pushed to its practical limits. Every measurement represented a snapshot of 3I Atlas against the background stars. Telescopes recorded the object's position in right ascension and declination, celestial coordinates analogous to longitude and latitude on Earth's surface. The precision required was staggering, with individual measurements accurate to fractions of an arcsecond. To understand what this means, imagine detecting the width of a human hair viewed from 20 kilometers away. That's the level of precision ground-based telescopes routinely achieve through careful calibration and statistical analysis of multiple measurements. This precision transforms fuzzy dots of light into precisely mapped trajectories tight enough to test fundamental physics. The global coordination required for this campaign showcased modern astronomy at its collaborative best. Northern Hemisphere observatories tracked 3I Atlas during summer months, while southern facilities took over as Earth's rotation brought different sky regions into view. Amateur astronomers contributed early observations that helped establish brightness patterns. Professional observatories provided the sub-arcsecond measurements needed for orbital refinement. Each positional measurement fed into increasingly sophisticated orbital models. Analysts at the Minor Planet Center compiled data from around the world, checking for systematic errors, rejecting obvious outliers, and building trajectory solutions that accounted for gravitational influences from the Sun, planets, and even major asteroids. The precision achieved by this global network explains how researchers could place such tight constraints on non-gravitational acceleration. When you have thousands of positions measured to milliseconds accuracy over months of observation, systematic deviations from gravitational trajectories become statistically significant, even if they're physically tiny. Small accelerations accumulate over time as position shifts that grow quadratically. After months of observation, even tiny non-gravitational forces should produce measurable orbital deviations. The upper limit of 15 millionths of a meter per day squared emerged from this analysis. Converting to more familiar terms gives roughly 2 billionths of a meter per second squared, about 1/10 millionth the acceleration in a gently moving elevator. This level of precision required treating Earth as a single planet-sized telescope with baseline separations spanning continents. Each observatory contributed its unique perspective to a collective endeavor exceeding what any single facility could accomplish. The data quality enabled tests of physics that were impossible just decades ago. 4,000 measurements from 227 observatories don't lie. They reveal truth through overwhelming statistical weight. July 21st, 2025. The Hubble Space Telescope pointed its advanced cameras toward 3I Atlas, capturing an image that would stop astronomers in their tracks. Instead of the classic comet appearance expected from an active icy body, Hubble revealed something that challenged basic intuitions about how debris behaves in space. The image showed a teardrop-shaped cocoon surrounding the nucleus, but with a pronounced feature that seemed to point the wrong direction. Most comet tails stream away from the Sun, swept outward by solar wind and radiation pressure. It's one of astronomy's most reliable visual signatures. Ancient Chinese astronomers used comet tail orientations as celestial compasses precisely because the physics is so predictable. But 3I Atlas displayed what observers described as a sunward glow, a forward-pointing feature that appeared to violate elementary physics. The anti-tail, as astronomers call these features, created an optical impression of material flowing toward the Sun rather than away from it. Anti-tails aren't completely unprecedented in solar system comets. They can result from viewing geometry when Earth's orbital position creates an illusion of sunward-pointing material. Larger dust particles following ballistic trajectories can also create apparent forward features when observed from specific angles. The mathematics work out perspective effects can fool the eye, and the phenomenon has been documented before. What made 3I Atlas's sunward glow notable was its prominence and persistence. This wasn't a brief geometric illusion that disappeared when viewing conditions changed. The forward-directed feature remained visible through multiple observations from different observatories over several weeks. The morphology suggested real physical processes, rather than simple perspective tricks. By late August, observations from the Gemini South Telescope revealed additional complexity. A more traditional antisolar tail began emerging, creating a dual structure with material apparently streaming both toward and away from the Sun. The morphology was evolving in real time as the object warmed while approaching closer to solar heating. This evolving appearance mattered because dust-to-gas ratios and grain dynamics affect where the brightness center falls relative to the actual nucleus. Astrometric measurements track this photocenter, the brightness-weighted average position. If three eye atlases' unusual morphology systematically shifts this apparent position, it could potentially bias the orbital solutions used to infer acceleration limits. The challenge lies in separating genuine orbital dynamics from photometric artifacts. Careful analysis must account for these effects to avoid drawing incorrect conclusions about the object's mass and behavior. Hubble's image revealed not just an interstellar visitor, but a puzzle wrapped in evolving dust dynamics and perspective geometry that complicated every subsequent measurement. August 6th, 2025. The James Webb Space Telescope turned its powerful infrared instruments toward 3I Atlas, beginning observations that would reveal the object's chemical identity in unprecedented detail. What JWST discovered painted a picture of formation conditions vastly different from anything in our solar system. The near-infrared spectrograph detected the expected water ice and water vapor signatures that characterize most comets. But the real surprise came in the carbon dioxide measurements. The ratio of carbon dioxide to water ranked among the highest ever measured in a comet at this distance from the Sun. This chemical signature carries profound implications about where and how 3I Atlas formed. Carbon dioxide freezes at much lower temperatures than water ice. In the cold outer regions of stellar systems, beyond what astronomers call the carbon dioxide snowline, temperatures drop below -125 degrees Celsius. Only in these frigid zones can carbon dioxide condense as solid ice alongside water. Most solar system comets formed closer to the Sun, where water ice dominates the composition. They contain some carbon dioxide, but typically in modest amounts compared to water. 3. I-Atlas's chemistry suggested formation in the extreme outer reaches of its parent system, in regions so cold that carbon dioxide became a major constituent rather than a minor component. The object essentially carries frozen memories of alien conditions, chemical fingerprints from a stellar environment billions of kilometers from whatever star gave it birth. These volatiles have remained preserved through potentially millions of years of interstellar travel, protected by the cold vacuum of space. The Spherex Space-based infrared telescope contributed additional observations, detecting an extended carbon dioxide coma reaching hundreds of thousands of kilometers from the nucleus. This massive invisible atmosphere surrounding the solid core was far larger than visible light images suggested. While optical telescopes showed a relatively compact, bright region, infrared revealed a vast envelope of gas that dwarfed the photogenic dust tail. JWST also detected carbon monoxide, another volatile that requires extremely cold formation temperatures. The combination of high carbon dioxide, significant carbon monoxide, and water created a chemical portrait that didn't match typical solar system comet templates. This wasn't just a visitor from another stellar system. This was a sample of matter that formed under conditions more extreme than anything in our planetary neighborhood. The chemistry added another layer to the mounting evidence that 3I Atlas represented something genuinely unusual. Not just massive, not just dynamically strange, but chemically exotic in ways that pointed toward formation environments at the cold, dark edges of alien solar systems. Very Large Telescope Spectroscopy in August of 2025 revealed something genuinely puzzling in 3I Atlas's expanding coma. Multiple nickel emission lines blazing prominently in the infrared spectrum, while iron remained conspicuously absent from the same wavelengths. This chemical asymmetry challenged basic assumptions about metal emissions in cometary environments. the observation itself was straightforward but striking. High-resolution spectrographs detected several nickel atomic transitions in the 700 to 900 nanometer wavelength range. These lines appeared clearly above noise levels, with signal strength that allowed quantitative analysis of nickel production rates and spatial distribution within the coma. Iron lines, which astronomers expected to find at nearby wavelengths, simply weren't there. The spectra showed noise levels consistent with upper limits on iron emission significantly below typical detection thresholds for comets at similar distances from the Sun. This wasn't just a failure to detect weak signals. It represented a genuine chemical peculiarity demanding explanation. Context makes the anomaly more significant. In meteoritic and cometary materials, nickel and iron typically coexist in similar chemical compounds. They form from similar nucleosynthetic processes in stellar cores, and often exist together in cosmic environments. Seeing abundant nickel without corresponding iron is like finding a forest full of oak trees, but no maples in regions where both species normally grow together. Traditional comet chemistry offers several potential explanations, though none perfectly matches the observed pattern. Photostimulated desorption represents one plausible mechanism. Solar ultraviolet radiation can break chemical bonds in surface materials, liberating atoms that would remain bound under purely thermal conditions. If 3I Atlas contains nickel-bearing compounds particularly susceptible to photodesorption, while iron-bearing phases remain more tightly bound, this could explain the chemical selectivity. Alternative hypotheses involve thermolysis of organometallic compounds, or metal-carbonyl complexes, that might exist in the nucleus. These materials can decompose at relatively low temperatures, releasing metal atoms through chemical breakdown rather than direct sublimation of refractory minerals. If nickel forms more volatile compounds than iron in this interstellar environment, differential release could produce the observed abundance pattern. What this chemistry does not prove deserves emphasis. Some commentators noted that nickel without iron resembles certain industrial alloy compositions and suggested technological interpretations. This represents a logical leap unsupported by spectroscopic evidence. Metallic emissions in cometary comas arise from well-understood atomic physics, not engineering processes. The universe contains plenty of natural processes capable of producing unexpected, elemental abundance patterns without invoking artificial origins. The nickel mystery added another layer to 3I Atlas's growing list of chemical anomalies. Through late July and August of 2025, 3I Atlas refused to settle into a stable appearance. Each new observation revealed changes in coma structure, tail geometry, and brightness distribution that complicated efforts to pin down the object's physical properties. This wasn't the predictable evolution of a typical comet warming as it approached the Sun. This was something more complex. Hubble's initial July observations showed the distinctive teardrop shape with prominent sunward glow. By the time Gemini South Telescope captured detailed images in late August, a more traditional anti-solar tail had begun emerging alongside the forward feature. The dual tail structure suggested that different dust populations were responding to solar radiation pressure in different ways. Large dust grains follow ballistic trajectories shaped primarily by the gravity and momentum they inherited when ejected from the nucleus. These particles can create curved tails that appear to point in unexpected directions depending on viewing geometry. smaller grains get swept more efficiently by solar radiation pressure, creating the classic straight tails, pointing directly away from the sun. The evolving morphology indicated that 3I Atlas was producing dust with a complex size distribution that changed over time as different volatile species began sublimating at different rates. Water ice becomes active around 3 astronomical units from the sun. Carbon dioxide sublimates at much greater distances. Exotic volatiles activate at their own characteristic temperatures as solar heating intensifies. This chemical evolution should correlate with morphological changes as different gas species drive different dust entrainment processes. The fact that the appearance continued evolving through the observation period suggested active sublimation, responding to changing thermal conditions as orbital geometry brought the object closer to solar heating. But the morphological complexity created problems for mass estimates. Astrometric measurements track the photocenter, the brightness-weighted average position of all the light coming from the object. If the coma structure shifts asymmetrically as dust production patterns change, this photocenter can move relative to the actual solid nucleus hidden beneath the haze. Systematic shifts in photocenter position could potentially mimic or mask real non-gravitational forces. Careful analysis must separate genuine orbital dynamics from photometric artifacts to avoid drawing incorrect conclusions about acceleration and therefore mass. The challenge lies in modeling dust dynamics, gas flow patterns, and viewing geometry effects simultaneously while the object continues evolving. Each new observation added data, but also added complexity. 3. I-Atlas wasn't cooperating with attempts to categorize it neatly. The morphology kept changing, the chemistry kept surprising researchers, and the fundamental question of what this object actually represented remained frustratingly open. Before October of 2017, interstellar objects existed only in theoretical papers and speculative conversations among astronomers. Everyone assumed they had to be out there, drifting through the space between stars. The mathematics of planetary system formation predicted their existence. Gravitational scattering during the chaotic, early phases of stellar system evolution should eject debris into interstellar space at predictable rates. But predictions and discoveries are different things. For all of human history, every asteroid and comet ever observed had been gravitationally bound to our Sun. Billions of years of orbital evolution had shaped their paths into ellipses that would repeat endlessly unless perturbed by planetary encounters or collisions. The solar system was a closed population, at least as far as observations could confirm. Theoretical estimates suggested that interstellar visitors should pass through the inner solar system relatively frequently, perhaps several per year for objects larger than 100 meters. But these estimates came with enormous uncertainties, spanning orders of magnitude. Some models predicted encounter rates 10 times higher, others 10 times lower. Without actual detections, the theoretical framework remained untested speculation. The detection problem was straightforward to understand but difficult to solve. Interstellar objects move fast, often traveling at speeds exceeding 20 kilometers per second relative to the Sun. They pass through the inner solar system quickly, visible for weeks or months, rather than the years or decades that characterize captured solar system comets. Survey telescopes need to scan large areas of sky repeatedly to catch these transient visitors during their brief passages. Before 2017, survey capabilities simply weren't up to the task. Telescopes with fields of view wide enough to scan substantial sky areas typically lacked the sensitivity to detect faint distant objects. Sensitive telescopes with narrow fields of view could see faint things, but only in tiny patches of sky, making random discoveries unlikely. The combination of wide field coverage and deep sensitivity needed to routinely find interstellar visitors didn't exist. The Pan-STARRS survey in Hawaii and the Catalina Sky survey in Arizona represented the first generation of facilities capable of systematic transient detection. These wide-field telescopes could image large sky areas to reasonable depths every few nights, building databases of moving objects that automated software could flag for human attention. But even with these capabilities coming online, astronomers expected their first interstellar detection to be relatively ordinary. A small comet-like object following a hyperbolic trajectory, behaving much like solar system comets, except for its exotic origin. Something familiar enough to recognize immediately as a visitor from beyond. Nobody was prepared for what actually arrived. October 19th, 2017, Pan-STARRS telescope in Hawaii detected a faint object moving rapidly across the sky. Within days, orbital calculations confirmed what astronomers had theorized about for decades but never witnessed. This object, designated one Oumuamua, was humanity's first confirmed interstellar visitor, but Oumuamua refused to behave according to expectations. Instead of displaying the cometary activity anticipated from an icy object warmed by the sun, it remained stubbornly inert. No visible coma, no gas jets, no dust tail, just a tumbling elongated body reflecting sunlight as it raced through the inner solar system at over 26 kilometers per second. The shape estimates added to the strangeness. Light curve analysis suggested an extremely elongated object, possibly 10 times longer than wide. Nothing in the solar system matched this geometry. Asteroids and comets come in various shapes, but Oumuamua's extreme elongation stood out as genuinely unusual. Then came the real surprise. Precise astrometric tracking revealed measurable non-gravitational acceleration. The object was deviating from a purely gravitational trajectory by small but statistically significant amounts. Yet no visible outgassing accompanied this acceleration. Oumuamua was being pushed by something, but telescopes couldn't see what. The scientific community erupted into creative speculation. Perhaps the object was outgassing hydrogen, a volatile so diffuse it wouldn't create a visible coma, but could still produce thrust. Maybe it was composed of nitrogen ice that sublimated invisibly. Some researchers proposed that solar radiation pressure, acting on an unusually flat geometry, could explain the acceleration without requiring outgassing at all. More exotic proposals suggested the object might be artificial, a light sail or probe from another civilization. While mainstream astronomy remained skeptical of technological explanations, the hypothesis gained enough attention to generate serious academic discussion about how one would distinguish natural from artificial interstellar objects. Oumuamua presented a paradox opposite to what 3I Atlas would later reveal. Where 3I Atlas shows activity without expected acceleration, Oumuamua showed acceleration without visible activity. The first interstellar visitor taught astronomers that expectations based on solar system experience might not apply to objects formed in alien stellar environments. By the time astronomers mobilized comprehensive observation campaigns, Oumuamua was already leaving. It faded from view in early 2018, carrying its mysteries back into interstellar space. The brief encounter left more questions than answers and demonstrated that humanity's detection infrastructure needed improvement if we wanted to study future visitors more thoroughly. The experience of missing crucial observations motivated upgrades to survey capabilities and rapid response protocols. Next time would be different, or so astronomers hoped. August 30th, 2019. Amateur astronomer Gennady Borisov, using his homemade telescope in Crimea, detected a faint, fuzzy object that would restore some comfort to the astronomical community. Unlike the enigmatic Oumuamua, this second confirmed interstellar visitor behaved exactly as theories predicted. 2. I Borisov, as it was officially designated, looked like a comet, acted like a comet, and followed all the rules that comets were supposed to follow. It displayed a visible coma from the moment of discovery. Spectroscopic observations revealed familiar water vapor and carbon monoxide emissions. The dust production rates matched expectations based on solar heating models. Everything about Borisov screamed ordinary. The nucleus measured roughly 1 kilometer across, typical for solar system comets discovered at similar distances from the Sun. As it approached closer to solar heating through late 2019, activity increased predictably. The tail grew longer, gas production rates accelerated, and most importantly, the non-gravitational acceleration matched theoretical predictions perfectly. For the first time, astronomers could directly compare an interstellar comet to solar system specimens and find essentially no differences. The chemical signatures looked familiar. The physical behavior followed established patterns. Borisov could have formed in our solar system, and nobody would have questioned its origins based on appearance or composition alone. This normality provided crucial scientific value. It demonstrated that at least some interstellar objects behave according to expectations based on solar system experience. The physics of ice sublimation, dust entrainment, and cometary activity appeared universal. Formation in another stellar system didn't necessarily produce exotic properties that violated familiar patterns. The reassurance went deeper. Borisov's predictable behavior validated decades of theoretical work on comet physics and planetary system formation. The models weren't fundamentally broken. Comets from other stellar systems could resemble comets from our own. The universe operated according to comprehensible rules that applied across interstellar distances. Professional observatories worldwide coordinated extensive campaigns to study Borisov before it disappeared back into the depths of space. Hubble Space Telescope captured detailed images of the nucleus and coma. Ground-based spectrographs analyze the chemical composition in unprecedented detail. The data harvest far exceeded what had been possible with Oumuamua's rapid surprise passage. By mid-2020, Borisov faded beyond detection limits, leaving behind a comprehensive dataset and a sense of scientific satisfaction. The second interstellar visitor had proven that not all such objects needed to be mysterious or challenging to fundamental assumptions. This comforting familiarity made 3 IATLAS's subsequent violations of expected behavior even more jarring. After Borisov demonstrated that interstellar comets could be normal, 3 IATLAS arrived to show that they could also be profoundly strange. The universe, it seemed, wasn't finished surprising us. 3 confirmed interstellar visitors in 8 years. 3 radically different objects that told conflicting stories about what drifts between the stars. The comparison reveals just how little humanity understands about the debris field that fills the space between stellar systems. Oumuamua showed acceleration without visible activity. Precise astrometric measurements detected non-gravitational forces pushing the object away from a purely gravitational trajectory. Yet telescopes saw no coma, no gas jets, no dust tail, nothing that could obviously explain the thrust. The object violated expectations by moving like a comet while appearing like an asteroid. 2. Borisov provided the opposite experience. It showed activity with expected acceleration. Gas production matched predictions. Dust emission followed theoretical models. And the non-gravitational forces appeared exactly where and when they should. Borisov behaved so normally it almost seemed boring by comparison to its enigmatic predecessor. Then came 3I Atlas with its own unique impossibility: activity without sufficient acceleration. The object produces vigorous outgassing that should create obvious orbital perturbations. Water vapor and carbon dioxide stream away at hundreds of meters per second. Yet, the expected rocket push remains below detection limits, suggesting mass so enormous it challenges population statistics. Each visitor occupies a different region of parameter space. Oumuamua sits in the high acceleration, low activity corner. Borisov falls on the expected trend line, where activity and acceleration correlate predictably. 3I Atlas occupies previously empty space, combining high activity with anomalously low acceleration. The sample size of 3 provides essentially zero statistical power for drawing conclusions about typical interstellar object characteristics. It's like trying to understand human height distribution after measuring only 3 randomly selected individuals. If one happened to be exceptionally tall, another average, and the third unusually short, you'd have no idea what typical actually means. Yet these 3 examples are all humanity has for understanding what wanders through interstellar space. Every theoretical framework, every population model, every prediction about encounter rates must be reconciled with this tiny sample that shows extreme diversity rather than comforting consistency. The progression from Oumuamua through Borisov to 3I Atlas reads less like accumulating knowledge and more like accumulating mysteries. Each new visitor raised different questions. Each challenged different assumptions. None provided the steady march toward understanding that scientists prefer. Perhaps the universe is telling us something through this diversity. Perhaps interstellar objects come in vastly different types, shaped by formation conditions and evolutionary processes that vary dramatically across stellar environments. Or perhaps we're witnessing statistical flukes, rare outliers that happen to arrive during humanity's first clumsy attempts at systematic detection. Either way, 3 visitors have given us 3 impossibilities, and the pattern, if there is one, remains frustratingly unclear. The population statistics problem keeps astronomers awake at night. If 3I Atlas truly masses 33 trillion kilograms or more with a 5-kilometer nucleus, it shouldn't have been the 3rd interstellar object humanity discovered. It should have been the 100th or the 1000th, discovered only after we'd catalogued dozens or hundreds of smaller visitors first. The physics of planetary system ejection strongly favors smaller objects. During the chaotic early phases of stellar system formation, massive bodies migrate through gravitational interactions that fling debris onto escape trajectories. These ejection events work like cosmic billiards, with planets acting as cue balls, striking smaller objects hard enough to launch them into interstellar space. Launch velocity scales inversely with object mass for a given gravitational encounter. A Jupiter-sized planet can easily eject kilometer-scale comets, but launching something the size of 3I Atlas requires much more specific geometric conditions and energy transfer. The process becomes exponentially less efficient as target mass increases. This means the interstellar medium should be populated primarily by small to moderate-sized debris. Objects measuring hundreds of meters to a few kilometers should vastly outnumber giants measuring 5 kilometers or larger. The size distribution should be steep, with each doubling of diameter corresponding to perhaps 10 times fewer objects in that size range. Detection biases should further favor finding smaller objects first, at least within certain size ranges. While the tiniest debris becomes invisible to current surveys, objects in the 100-meter to kilometer range should be detectable when they pass through the inner solar system and develop visible comas. Brightness increases with size, but not fast enough to overcome the numerical advantage of smaller populations. Yet here we are, 3 confirmed detections, and the latest is potentially orders of magnitude more massive than its predecessors. It's like conducting a census by randomly sampling 3 people and finding that the third happens to be 8 feet tall. Possible, but statistically uncomfortable. Several explanations could resolve this paradox. Perhaps detection geometry systematically favors certain object classes over others. Maybe smaller interstellar debris gets destroyed more efficiently during million-year journeys through space, biasing the arriving population toward robust, massive specimens. Survey selection effects might preferentially detect unusually active objects regardless of their intrinsic size. Or perhaps 3I Atlas represents a genuine statistical fluke, an extreme outlier that happened to appear during humanity's first systematic surveys. Such events occur by definition in the tails of any distribution. Their rarity makes them memorable when they do appear, but doesn't necessarily indicate problems with underlying theoretical frameworks. Still, the uncomfortable question persists. If massive visitors like 3I Atlas exist, where are all the smaller cousins we expected to find first? The conservative scientific position maintains that 3I Atlas, despite its unusual characteristics, remains a natural object governed by well-understood physics. This framework doesn't require exotic new theories or revolutionary interpretations. It simply pushes conventional comet physics into unexplored territory. The mass estimates depend heavily on assumptions about gas production rates and momentum transfer efficiency. If these assumptions prove even slightly incorrect, the inferred mass could change dramatically. Perhaps the outflow rates are lower than spectroscopic observations suggest. Maybe gas escape occurs through distributed seepage rather than collimated jets, reducing momentum transfer efficiency. Small changes in underlying parameters could bring the mass estimates down to less anomalous values. Dust grain properties offer another avenue for natural explanation. If 3I Atlas produces unusually large dust particles, they would scatter sunlight differently than typical comet dust. Forward scattering by specific grain size distributions could create brightness enhancements that appear to violate basic physics, but actually result from well-understood optical effects. The sunward glow might be pure geometry and particle physics, rather than evidence of exotic behavior. The carbon dioxide-rich chemistry, while unusual, doesn't require abandoning natural formation scenarios. Some regions of protoplanetary disks reach temperatures cold enough for carbon dioxide to become a dominant ice component. Objects forming beyond the carbon dioxide snowline would naturally acquire the enriched volatile ratios observed in 3I Atlas. The chemistry indicates formation in extremely cold conditions, but doesn't necessarily imply anything more exotic than distant birthplaces in alien stellar systems. The nickel without iron emission pattern challenges assumptions, but doesn't definitively prove artificial origins. Differential photodissorption rates, unusual organometallic compounds, or selective thermal release mechanisms could all produce asymmetric metal emissions through purely natural chemistry. Laboratory experiments and detailed modeling might eventually identify specific processes that explain the observations without invoking technology. Even the population statistics paradox admits conventional resolution. Survey selection effects might be more severe than recognized. Perhaps detection methods strongly favor ecliptic aligned objects with favorable viewing geometries, like 3I Atlas. Maybe small interstellar debris suffers higher destruction rates during transit through the harsh interstellar medium. Cosmic ray erosion, micrometeorite, impacts, and sublimation driven by chance stellar encounters could preferentially remove smaller objects from the observable population. The fundamental principle of scientific conservatism holds that extraordinary claims require extraordinary evidence. Unusual observations deserve investigation and explanation, but don't automatically justify abandoning established frameworks. Natural processes operating under extreme or unusual conditions can produce surprising results without requiring new physics. 3I Atlas might simply represent the tail end of the comet size distribution, a rare, massive specimen that happens to have arrived during humanity's initial surveys. Statistical flukes occur. Early samples often include outliers that disappear into more typical distributions as sample sizes grow. The Vera Rubin Observatory will soon discover dozens or hundreds of interstellar visitors, providing the statistical power to determine whether 3I Atlas represents typical mass or genuine anomaly. Until then, the conservative explanation remains viable. Unusual doesn't mean impossible. Challenging doesn't mean revolutionary. Sometimes a comet is just a comet, even if it's the largest, strangest comet we've encountered so far. One of the most intriguing theoretical frameworks for understanding massive interstellar visitors, like 3I Atlas, comes from planetary formation research. The planet seeding hypothesis suggests that interstellar objects captured by young stellar systems could bypass traditional formation bottlenecks and jumpstart giant planet growth during the brief window when protoplanetary disks retain sufficient mass to support rapid accretion. Traditional planet formation faces a significant timing problem. Giant planets must grow to substantial sizes before their parent protoplanetary disks dissipate through photoevaporation and stellar accretion. This process typically occurs within 5 to 10 million years of stellar birth, creating tight constraints on how quickly planetary cores can accumulate enough mass to trigger runaway gas accretion. Core accretion models struggle with what astronomers call the meter-size barrier. Growing planetesimals feel significant drag from disk gas, causing orbital decay that prevents growth to planet-size scales. Small debris spirals into the parent star through aerodynamic forces before gravitational binding can create larger bodies. The timing problem becomes acute when you calculate how long traditional processes need to build kilometre-scale cores from dust grains. Interstellar object capture offers an elegant solution. If young stellar systems can gravitationally capture pre-existing kilometre-scale objects from the interstellar medium, these ready-made seeds bypass the slow growth phase entirely. A captured visitor already possesses sufficient mass to resist aerodynamic drag while providing gravitational scaffolding for rapid planet assembly. The mechanism works through gravitational focusing, effects during close encounters between interstellar visitors and young stellar systems. More massive stars create deeper gravitational potential wells that increase capture cross-sections for passing objects. Dense stellar forming regions provide both high encounter rates with interstellar debris and gravitational environments favorable for permanent capture. Recent modeling indicates that massive stars capture interstellar objects more efficiently than lower mass stellar systems, creating a potential correlation between stellar mass and giant planet occurrence that matches observational trends in exoplanet demographics. The chemistry connection adds plausibility to seeding scenarios involving 3I Atlas specifically. Objects carrying carbon dioxide, rich volatile compositions formed in extremely cold outer regions of their parent systems. A captured interstellar visitor could introduce chemical diversity into its new host disk, potentially explaining compositional variety observed in exoplanet atmospheres. Conference presentations in 2025 provided updated simulations supporting capture scenarios. The calculations suggest young stellar systems could capture interstellar objects at rates sufficient to influence planet formation outcomes. The process becomes most efficient during the first few million years, when stellar systems retain circumstellar disks massive enough to support rapid accretion onto captured seeds. Population statistics become crucial for evaluating seeding hypothesis viability. If the Vera Rubin Observatory discovers numerous massive interstellar visitors over the next decade, capture rates in young stellar systems become statistically plausible. If 3I Atlas proves exceptionally rare, seeding scenarios lose credibility due to insufficient raw material availability. The revolutionary aspect of planet seeding lies in reframing how we think about planetary system formation. Instead of isolated stellar systems building planets entirely from local materials, the hypothesis introduces galactic-scale material exchange. Interstellar visitors become cosmic messengers carrying matter between stellar environments, mixing chemical signatures from multiple formation sites across vast distances. If correct, planet seeding means that giant planets throughout the galaxy might contain cores captured from interstellar space, refugees from other stellar systems that found new homes and triggered planet formation cascades. The technological interpretation of 3I Atlas emerges from a convergence of unusual characteristics that, when viewed collectively, challenge conventional natural explanations. The hypothesis doesn't claim definitive proof of artificial origins, but rather asks whether the accumulating anomalies warrant serious investigation of possibilities beyond standard comet physics. The orbital geometry provides the foundation for these questions. 3I Atlas approaches the solar system with an inclination of just 4.1 degrees relative to the planetary plane. Random arrivals from arbitrary interstellar directions should produce inclinations distributed across all possible angles. The probability of achieving alignment this close to the ecliptic by pure chance, sits around 1 in 500. Not impossible, but statistically noteworthy. Harvard astronomers have been among the most prominent voices advocating for taking technological possibilities seriously. The approach involves calculating probabilities for various natural scenarios and comparing them with alternative explanations when conventional physics appears insufficient. This represents scientific hypothesis generation rather than evidence-free assertion, though the boundary between legitimate speculation and premature conclusion can become blurred in public discourse. The mass paradox contributes to technological speculation through elimination of straightforward natural explanations. If 3I Atlas truly weighs tens of billions of tons with minimal non-gravitational acceleration despite active outgassing, conventional comet physics struggles to accommodate such behavior. Some have suggested that controlled propulsion could explain the disconnect between visible activity and missing orbital perturbations, though natural alternatives involving unusual dust dynamics or exotic ice chemistry remain viable. Testable predictions distinguish scientific speculation from unfounded conjecture. If 3I Atlas were indeed artificial, it might exhibit sudden trajectory changes beyond what outgassing physics predicts. Such deviations would appear as unexplained accelerations in continued astrometric monitoring. Alternative signatures might include non-thermal emission patterns detectable by infrared telescopes, coherent radio transmissions, or polarization characteristics inconsistent with natural dust scattering. Current observational capabilities make detecting such signatures challenging, but they represent concrete tests that could distinguish natural from artificial explanations. The absence of these definitive signals so far suggests that current observations, while interesting, remain insufficient to support extraordinary conclusions about technological origins. NASA and international space agencies maintain positions of treating 3I Atlas as natural unless compelling data suggests otherwise. This represents standard scientific conservatism, assuming conventional explanations until observations definitively rule them out. The agencies continue monitoring the object with available assets while avoiding premature conclusions. Congressional interest reached official levels when representatives sent letters urging detailed study of mission concepts that could investigate 3I Atlas more closely. This political attention underscores extraordinary public fascination surrounding the object and reflects growing recognition that such opportunities may not arise again for decades. The technological hypothesis serves important functions in scientific discourse, even if ultimately disproven. It provides alternative frameworks for interpreting unusual data, forces more rigorous analysis of conventional explanations, and motivates better observations to distinguish between competing models. Science benefits from intellectual diversity and skeptical examination of assumptions. However, maintaining appropriate skepticism requires distinguishing between legitimate scientific speculation and conspiracy thinking. The technological interpretation represents testable hypothesis generation backed by calculations and predictions, not baseless assertion. But extraordinary claims demand extraordinary evidence, and current observations haven't yet crossed that threshold. The question remains open, awaiting data that could tip the scales decisively in one direction or another. Beyond conventional comet physics and technological speculation lies a third category of explanations that invoke exotic physical processes operating at scales, or in regimes poorly understood by current science. These alternatives represent the frontier where established physics meets genuine uncertainty about how nature behaves under extreme conditions. Dark matter interactions provide one speculative framework. If 3I Atlas contains significant amounts of dark matter bound within its structure, the gravitational behavior could deviate from expectations based purely on visible matter. Dark matter comprises roughly 85% of the universe's total mass, but interacts only through gravity, making it effectively invisible to telescopes. An object with anomalous dark matter content might show gravitational signatures inconsistent with its visible mass. The challenges with dark matter explanations are substantial. Current understanding suggests dark matter doesn't clump efficiently on small scales, like individual comets. The physics that prevents dark matter from collapsing into compact objects would also prevent it from being captured and retained by something the size of 3I Atlas. While theoretically interesting, dark matter scenarios require mechanisms that don't currently exist in established physics. Modified gravity theories offer another exotic possibility. At extremely large scales like galaxy clusters, some researchers have proposed that gravitational physics might deviate slightly from Einstein's general relativity. If similar modifications operate on small scales under specific conditions, they could potentially affect how momentum transfer works during outgassing events. The object might experience forces that differ from standard Newtonian predictions. The problem with modified gravity explanations is that they're designed to explain large-scale cosmic phenomena, not comet dynamics in the inner solar system. Extending these theories to 3I Atlas requires assumptions about physics in regimes where they've never been tested. It's speculation. Built on speculation, scientifically interesting, but empirically unsupported. Quantum effects in macroscopic objects represent a third exotic avenue. Standard physics treats large objects as purely classical systems, where quantum mechanics becomes irrelevant. But if 3I Atlas somehow maintains quantum coherence across macroscopic scales, its behavior might deviate from classical predictions in subtle ways. This speculation ventures into territory where current physics provides little guidance. The appeal of exotic physics explanations lies in their ability to accommodate observations that challenge conventional frameworks. If standard comet physics can't explain 3I Atlas, perhaps the solution involves physics we don't yet understand. This reasoning has historical precedent. Anomalies in Mercury's orbit eventually revealed limitations in Newtonian gravity, requiring Einstein's general relativity for proper explanation. However, invoking exotic physics should be a last resort after exhausting conventional alternatives. The history of science shows that most anomalies eventually receive explanations within established frameworks. Unusual observations typically reveal gaps in application rather than fundamental flaws in underlying theories. 3I Atlas might push comet physics into unexplored parameter space without requiring new fundamental physics. The exotic alternatives remain scientifically interesting as thought experiments that probe the boundaries of current understanding. They highlight what we don't know about physics under extreme conditions. But they also demonstrate the danger of prematurely abandoning established frameworks when observations become challenging. Sometimes the simplest explanation, even if uncomfortable, proves correct. Sometimes nature operates in familiar ways under unfamiliar circumstances, and sometimes patience and better data resolve apparent impossibilities without requiring revolutionary new physics. Occam's razor suggests that the simplest explanation, requiring the fewest assumptions, usually proves correct. But applying this principle to 3, I-Atlas creates a philosophical puzzle. Which explanation actually requires fewer assumptions? Natural but unprecedented comet physics, or artificial but unproven technology? The natural explanation requires accepting that 3 I-Atlas represents an extreme outlier in the interstellar object population. A massive comet with unusual chemistry, strange morphology, and anomalous dynamics that nonetheless operates through conventional physical processes. This framework adds no new physics, but demands belief in a statistical coincidence, finding the giant specimen third before adequately sampling smaller populations. It also requires faith that current understanding of outgassing dynamics, momentum transfer, and coma photometry contains gaps large enough to explain away the acceleration paradox. Perhaps dust grain properties differ more dramatically than recognized. Maybe gas escape mechanisms involve processes not yet incorporated into standard models. The physics remains conventional, but the application stretches into unexplored territory. The technological explanation requires accepting that intelligent civilizations exist elsewhere in the galaxy, and that they've developed capabilities to send objects on interstellar trajectories. It demands belief that such civilizations would choose to send visitors through our solar system, and that we'd happen to detect one during humanity's first few years of systematic interstellar object surveys. It also requires mechanisms for controlled propulsion that leave no obvious signatures beyond the missing acceleration. No radio transmissions, no artificial spectral features, no engineering structures visible in telescope images. The technology would need to be sophisticated enough to appear almost entirely natural, while still producing the observed anomalies. Both explanations pile assumption on assumption. The natural framework stacks statistical improbabilities and unexplored physics. The technological framework stacks sociological speculation and invisible engineering. Neither path leads to comfortable simplicity. Scientific conservatism traditionally favors natural explanations as default positions. The burden of proof falls on extraordinary claims, and artificial origins certainly qualify as extraordinary. This principle has served science well historically, preventing premature abandonment of established frameworks when observations become challenging. But conservatism can also calcify into dogma if taken too far. The history of science includes examples where entrenched positions delayed acceptance of revolutionary discoveries. Continental drift, bacterial ulcers, and meteorites all faced skepticism from scientific establishments before overwhelming evidence-forced paradigm shifts. The key distinction lies in evidence quality. Revolutionary claims eventually succeeded because they accumulated data that definitively ruled out conventional alternatives. 3. I-Atlas hasn't yet reached that threshold. The observations are unusual, but not inexplicable through natural processes. The anomalies challenge assumptions, but don't demolish established physics. Perhaps the real lesson involves recognizing that Occam's razor doesn't always provide clear guidance when comparing radically different frameworks. The principle works best when evaluating variations within a single explanatory paradigm. Natural explanation A versus natural explanation B can be compared by counting assumptions. But natural versus technological explanations operate in such different conceptual spaces that simple assumption counting becomes meaningless. The dilemma might be asking the wrong question. Instead of debating which framework is simpler, perhaps we should focus on which makes testable predictions that future observations could confirm or refute. Science progresses through falsifiable hypotheses, not philosophical arguments about simplicity. 3-Eye Atlas will eventually reveal its nature through continued observation. The object follows physical laws, whether those laws involve conventional comet dynamics or something more exotic. Data, not debate, will ultimately resolve the Occam's razor dilemma. October 3rd, 2025. 3-Eye Atlas passes within 30 million kilometers of Mars, creating an unprecedented opportunity for multi-vantage point observations of an interstellar visitor. This encounter distance of roughly 0.2 astronomical units places the object well within operational range of Mars-orbiting spacecraft, potentially providing perspectives impossible from Earth-based telescopes. The European Space Agency operates 2 missions around Mars that could potentially observe 3-Eye Atlas during its passage. Mars Express, launched in 2003 and still functioning after more than 2 decades, carries imaging systems and scientific instruments. The Trace Gas Orbiter, which arrived in 2016 as part of the ExoMars program, provides additional observational capabilities. Both spacecraft face operational constraints and power limitations that require careful mission planning. NASA's MAVEN orbiter, studying Martian atmospheric escape since 2014, represents another potential observer. While primarily designed for atmospheric research rather than deep space observations, MAVEN's instruments might contribute to the campaign if mission managers can accommodate pointing requirements and data collection priorities. The different viewing geometry offers crucial advantages over Earth-based observations. From Mars, 3-Eye Atlas appears at different phase angles, illumination conditions, and sky positions than visible from our planet. These perspective differences could reveal dust scattering properties, coma asymmetries, and brightness variations that remain hidden from terrestrial viewpoints. The scientific value extends beyond simple imaging. Photometric measurements from Mars' orbital perspective would provide independent constraints on activity levels and help test theoretical frameworks connecting visible outgassing with inferred mass. Any observations would complement Earth-based data and potentially resolve discrepancies in brightness and morphology assessments. Coordination between Mars assets and ground-based telescopes requires precise timing protocols. The light travel time between Earth and Mars during the encounter period is approximately 16 minutes, complicating real-time coordination but allowing planned observation sequences designed to maximize scientific return. Communication planning becomes crucial for transmitting data back to Earth within reasonable timeframes. The encounter distance poses no risk to Mars missions. 30 million kilometers represents roughly 75 times the distance between Earth and Moon. Close by astronomical standards, but presenting zero collision hazard or operational threat to orbiting spacecraft. The observation opportunity comes with essentially no mission risk. Historical precedent exists for Mars-based observations of solar system objects. Mars orbiters have occasionally observed asteroids and comets when geometric conditions proved favorable. But none of these previous observations involved interstellar visitors with the unusual characteristics attributed to 3 Eye Atlas. The Mars encounter represents humanity's first chance to observe an interstellar object from multiple solar system locations simultaneously. Even limited data would demonstrate coordination capabilities that will become routine as interplanetary missions proliferate, and detection rates for transient phenomena increase throughout the coming decades. 3. Eye Atlas reaches its closest approach to the Sun on the far side from Earth's perspective, creating a months-long observational blackout that has fueled both legitimate scientific concern and unfounded speculation about intentional evasion. The timing results purely from orbital mechanics, not conscious navigation, but the geometry creates genuine challenges for continuous monitoring. Perihelion, the point of closest solar approach, occurs when 3 Eye Atlas swings behind the Sun as viewed from Earth. During this period, the object becomes lost in solar glare, invisible to ground-based telescopes that cannot point close enough to the Sun without risking damage to sensitive instruments. Space-based observatories face similar constraints, with operational limits on how close to the Sun they can safely observe. This observational gap matters scientifically because perihelion represents the most dynamically active phase. Solar heating reaches maximum intensity, driving sublimation rates to peak values. Gas production accelerates, dust emission intensifies, and any non-gravitational forces should become most pronounced. Missing observations during this critical period leaves gaps in understanding how 3 Eye Atlas responds to maximum thermal stress. Some media coverage has described the perihelion timing as intentional evasion, suggesting the object deliberately chose a trajectory that hides behind solar glare during its most active phase. This interpretation fundamentally misunderstands orbital mechanics. 3. Eye Atlas follows a hyperbolic path determined entirely by its initial velocity vector when entering the solar system and the gravitational influence of the Sun and planets. The object has no agency, makes no choices, and cannot alter its trajectory except through natural forces like outgassing or gravitational perturbations. Solar system geometry places perihelion on the Sun's far side, relative to Earth, purely through mathematical coincidence, based on where the object happened to be when it entered our cosmic neighborhood millions of years ago. However, one spacecraft provides unique coverage during the blackout period. Parker Solar probe, designed to study the Sun's corona from unprecedented proximity, carries the WISPER instrument that can potentially observe 3 Eye Atlas from solar perspectives, unavailable to Earth-based telescopes. These observations could reveal activity patterns or morphological changes invisible from terrestrial viewpoints. The different viewing geometry might resolve questions about the unusual sunward glow and evolving tail structure that have puzzled ground-based observers. Seeing 3 Eye Atlas from the Sun's perspective during peak activity could provide crucial constraints on dust dynamics and gas flow patterns that remain ambiguous from Earth's limited vantage point. The perihelion blackout demonstrates how solar system geometry affects our ability to study transient visitors. It's not evasion or conspiracy, just the simple reality that objects passing through the inner solar system sometimes move behind obstacles that block our view. This limitation affects all astronomical observations and requires creative solutions using multiple spacecraft at different locations. March 16th, 2026. 3 Eye Atlas will pass within 53.6 million kilometers of Jupiter, creating what might be humanity's best chance for close-up investigation of an interstellar visitor. Multiple research papers have outlined ambitious mission concepts for redirecting NASA's Juno spacecraft toward an intercept trajectory using gravitational assist maneuvers and remaining fuel reserves. The orbital mechanics involved would require what aerospace engineers call an Oberth effect maneuver. By firing spacecraft engines at the point of closest approach to Jupiter, where orbital velocities reach maximum values, each unit of propellant provides maximum momentum change for trajectory modification. The technique amplifies thrust effectiveness by exploiting the deep gravitational well. Juno currently orbits Jupiter, conducting extended mission operations focused on detailed mapping of the gas giant's gravitational field, magnetic environment, and atmospheric dynamics. Redirecting toward 3I Atlas would necessarily curtail these investigations in favor of interstellar visitor science. The decision involves trading primary science objectives against once-in-a-lifetime opportunities for breakthrough discoveries. Fuel limitations present the primary technical constraint. Juno was not designed for major trajectory changes and carries limited propellant reserves for station keeping and orbital adjustments around Jupiter. Reaching 3I Atlas would require expenditure of essentially all remaining fuel, ending any possibility of returning to Jupiter science operations. Engineering assessments must evaluate whether propulsion systems can deliver sufficient velocity change within available fuel margins. The scientific payoff from successful in situ sampling would dwarf anything achievable through remote observations. Juno's instruments could potentially analyze dust composition directly, measure grain size distributions, determine isotopic ratios, and characterize magnetic properties. Data quality levels that remain impossible using ground-based telescopes or even space-based observatories operating from Earth vicinity. Direct sampling would provide definitive tests of chemical anomalies inferred from spectroscopic observations. The nickel without iron puzzle, the carbon dioxide, rich ice composition, and other unusual characteristics could be verified or refuted through direct contact with the object's coma and debris trail. Such measurements would settle questions about 3I Atlas's nature that might otherwise remain unresolved for years. Congressional interest reached official levels when representatives sent letters to NASA urging detailed study of repurposing Juno for interstellar object investigation. This political attention underscores extraordinary public fascination surrounding 3I Atlas and reflects growing recognition that such opportunities may not arise again for decades or longer. Risk-benefit analysis for mission repurposing involves trading guaranteed Jupiter science against uncertain but potentially transformative gains from direct interstellar visitor investigation. The decision timeline will unfold over coming months as NASA evaluates technical feasibility, scientific merit, and resource implications. Whether through direct spacecraft encounter or continued remote observations, the Jupiter phase of 3I Atlas's journey will provide crucial tests of theoretical frameworks attempting to explain its unusual properties. The Juno intercept proposal represents more than just another spacecraft mission. It embodies humanity's first realistic chance to touch an object that formed around another star, to sample material that has traveled through interstellar space for potentially millions of years, to answer questions that remote observations can only hint at through fuzzy spectral lines and ambiguous brightness measurements. Consider what direct sampling could accomplish. Juno carries a suite of instruments originally designed to study Jupiter's environment, but adaptable to investigating 3I Atlas at close range. The magnetometer could detect magnetic field signatures that might reveal internal structure or composition. Charged particle detectors could analyze the ionized component of the coma, measuring plasma properties and particle energy distributions. Most importantly, direct passage through the debris trail would allow collection of dust grains for compositional analysis. While Juno lacks dedicated sample return capabilities, its instruments could characterize grain properties in real time through impact detection, spectroscopic analysis, and mass spectrometry of volatilized material. These measurements would provide ground truth for all the remote observations that have generated so much speculation. The isotopic ratios alone could revolutionize understanding. Every stellar system produces slightly different isotopic signatures based on the nuclear processes that created its parent star and the subsequent chemical evolution of its protoplanetary disk. Measuring oxygen isotope ratios, carbon isotope distributions, and heavy element abundances in 3I Atlas would provide definitive fingerprints of its formation environment. These isotopic measurements could confirm or refute the exotic chemistry suggested by JWST observations. If 3I Atlas truly formed in extremely cold regions beyond the carbon dioxide snowline, its isotopic ratios should reflect those formation conditions. Deviations from solar system norms would prove definitively that this object came from a chemically distinct environment shaped by different stellar processes. The nickel without iron mystery could be resolved through direct measurement. Remote spectroscopy reveals what atoms emit light in the coma, but provides limited information about the chemical compounds actually present in the nucleus. Direct sampling could identify specific minerals, organic compounds, and metal-bearing phases that explain the unusual emission patterns. Laboratory-style analysis in space, answering questions that Earth-based telescopes cannot address. Grain size distributions represent another measurement impossible from remote observation. Visible light images and spectroscopy provide indirect evidence about dust properties, but cannot definitively determine whether 3I Atlas produces unusual particle populations. Direct passage through the coma would measure grain sizes directly through impact sensors and dust detectors, testing hypotheses about forward scattering and morphological anomalies. The magnetic field measurements could prove particularly revealing. Some researchers have speculated that unusual internal structure might contribute to 3I Atlas's anomalous dynamics. If the object contains significant amounts of metallic phases or possesses unexpected density distributions, magnetic field measurements during close approach might detect these features through perturbations in the local magnetic environment. Thermal emission patterns during close flyby would constrain surface properties and heat distribution across the nucleus. Infrared imaging could reveal hotspots where gas jets emerge, cold regions where fresh ice remains exposed, and temperature gradients that trace solar heating patterns. These thermal maps would test models of subsurface heat flow and volatile migration that remain purely theoretical without direct measurement. The mission timeline adds urgency to decision-making. Redirecting Juno requires months of planning, trajectory calculation, and spacecraft preparation. The orbital mechanics window closes based on fuel constraints and geometric considerations. Waiting too long eliminates the opportunity entirely. NASA must decide relatively soon whether to attempt this unprecedented intercept or continue with standard Jupiter operations. Alternative mission concepts exist, but face greater challenges. Designing and launching a dedicated interstellar object interceptor would require years of development and enormous expense. By the time such a mission reached 3I Atlas, the object might have moved too far from the Sun for effective observation. Other existing spacecraft, like Psyche or Lucy, follow trajectories too divergent for practical redirection toward 3I Atlas. The political dimension cannot be ignored. Congressional interest reflects public fascination with potential interstellar visitors and the prospect of definitive answers to questions about 3I Atlas's nature. Successfully executing a Juno intercept would demonstrate American leadership in space exploration, while potentially yielding discoveries that reshape understanding of the galaxy we inhabit. The risk calculation involves weighing certain loss of planned Jupiter science against possible transformative gains from interstellar object investigation. Juno has already exceeded its primary mission objectives many times over. The extended mission provides valuable but incremental advances in understanding Jupiter's environment. 3I Atlas offers once-in-a-generation opportunity for breakthrough discovery that transcends incremental progress. History might judge this decision as one of the defining moments in early 21st century space exploration. The choice to pursue close encounter with an interstellar visitor, or to let the opportunity pass, will reveal how humanity balances conservative science against revolutionary possibility. When both paths demand resources we can spend only once. While spacecraft missions capture headlines, the real foundation of 3I Atlas science comes from coordinated ground-based observations involving hundreds of telescopes and thousands of hours of observation time. This campaign represents modern astronomy at its collaborative peak, transforming Earth itself into a planet-sized observatory with eyes constantly trained on the interstellar visitor. The James Webb Space Telescope continues periodic observations, building temporal coverage of chemical evolution as the object warms approaching the Sun. Each spectroscopic sequence adds data points to models tracking how volatile production rates change with solar distance. The infrared sensitivity reveals molecular transitions invisible to optical telescopes, particularly the extended carbon dioxide coma that dwarfs visible features. Hubble Space Telescope provides complementary visible and ultraviolet observations that track dust morphology and brightness variations. The images document how tail structures evolve over weeks and months, providing crucial context for interpreting the unusual sunward glow and emerging antisolar features. High-resolution imaging resolves coma structure at scales impossible from ground-based facilities. The Very Large Telescope in Chile continues spectroscopic monitoring, tracking the nickel emission mystery and searching for additional chemical anomalies that might emerge as thermal conditions change. Each spectrum provides a chemical snapshot, building a library of compositional data that chronicles 3I Atlas's response to varying solar heating intensity. Gemini North and South telescopes contribute imaging and spectroscopy from both hemispheres, ensuring continuous coverage as Earth's rotation carries different observatories into optimal viewing positions. The coordination eliminates gaps that would occur if single facilities attempted comprehensive monitoring alone. Ground-based radio telescopes search for molecular emission lines that trace gas production directly, while 3I Atlas remains relatively faint at radio wavelengths. sensitive arrays can potentially detect transitions from molecules like carbon monoxide and methanol that provide independent constraints on outgassing rates. Amateur astronomer networks contribute photometry and morphology observations that extend temporal coverage beyond what professional facilities can provide alone. These observations, while individually less precise than major observatory measurements, collectively fill critical gaps in brightness monitoring and help characterize variability patterns. Data sharing protocols ensure that observations flow rapidly to central archives where researchers worldwide can access results. The Minor Planets Center compiles astrometric measurements. Spectroscopic databases archive chemical observations. Image repositories collect morphological data. This distributed infrastructure transforms individual observations into collective knowledge. The Ground Truth Campaign will continue through 3I Atlas's entire passage, building a comprehensive observational record that future researchers will mine for decades. Every spectrum, every image, every positional measurement contributes to understanding this enigmatic visitor. The accumulated data will outlive current theoretical debates, providing empirical foundation for whatever explanations eventually emerge. If 3I Atlas truly represents typical interstellar debris rather than an extreme outlier, the implications for planetary formation theory extend throughout the galaxy. Every assumption about how stellar systems eject material, how that material survives interstellar transit, and what arrives at neighboring systems requires re-evaluation in light of massive visitors like this enigmatic object. Traditional models focus on ejection of modest-sized debris through planet-to-planet gravitational scattering. Jupiter-sized worlds fling kilometer-scale comets onto escape trajectories during the chaotic early phases of system formation. These ejected objects populate the interstellar medium with material that carries chemical signatures from their birth environments. The process operates continuously across billions of stellar systems over cosmic time. But ejecting 5-kilometer objects weighing tens of trillions of kilograms requires far more specific conditions. Close encounters between forming planets and massive debris must transfer enormous momentum without destroying the target through tidal forces. The geometry needs precise alignment. The timing must occur during narrow windows when such large objects exist but haven't yet been consumed by growing planets. If massive interstellar visitors prove common, ejection mechanisms must be more efficient than current models predict. Perhaps stellar flybys during the clustered formation phase contribute more significantly than recognized. Maybe disk instabilities in massive protoplanetary systems eject larger objects than traditional planet scattering processes. The theoretical frameworks might need fundamental revision to accommodate observed visitor demographics. The survival question becomes equally important. Million-year journeys through interstellar space expose objects to cosmic ray bombardment, micrometeorite erosion, and occasional close passes by other stellar systems. Small debris might not survive these hazards intact, biasing the arriving population toward robust, massive specimens that resist destruction. This survivorship bias could explain why 3I Atlas appears so anomalously large. Perhaps the interstellar medium contains abundant small debris that gets sandblasted away before reaching neighboring systems. Only the massive survivors complete the journey, creating a delivered population skewed toward giants, even if the ejected population favors smaller objects. The planet seeding implications grow more significant if massive visitors prove common. Young stellar systems, capturing 5-kilometer seeds, would gain enormous head starts in planet formation. These ready-made cores bypass the slow accumulation phase, immediately providing gravitational scaffolding for rapid gas accretion. The process could explain how giant planets form quickly enough to capture substantial atmospheres before protoplanetary disks dissipate. Understanding 3. I-Atlas's true nature and prevalence will reshape models of how planets form throughout the galaxy. The stakes extend beyond academic curiosity to fundamental questions about the cosmic processes that create habitable worlds. The Vera Rubin Observatory represents a quantum leap in humanity's ability to detect and study transient phenomena throughout the solar system and beyond. When fully operational, this facility will scan the entire southern sky every few nights for 10 years, potentially discovering hundreds or thousands of interstellar objects, and transforming the field from anecdote-based speculation into robust statistical science. The Legacy Survey of Space and Time, Rubin's primary mission, will capture images of unprecedented depth across enormous sky areas. The combination of wide field coverage and sensitivity means objects like 3I Atlas will no longer represent rare surprises, but regular discoveries that accumulate into meaningful population samples. Within a decade, astronomers will have enough data to answer questions that currently remain pure speculation. If 3I Atlas represents typical interstellar visitor mass, Rubin should detect similar giants regularly. Discovery rates might reach dozens per year for objects in this size range passing through the inner solar system. The statistical sample will quickly reveal whether massive visitors are common, or whether 3I Atlas truly represents an extreme outlier that happened to arrive during humanity's initial surveys. Conversely, if Rubin discovers primarily smaller interstellar objects, the mass distribution will shift back toward conventional expectations. 3I Atlas would be revealed as a statistical fluke, a tail-end specimen from a population that actually follows predicted size distributions. The accumulating data would restore confidence in ejection models and population synthesis frameworks that currently struggle to accommodate such massive early discoveries. The survey will also detect interstellar visitors at much greater distances from the Sun, providing warning time for detailed observation campaigns. Current discoveries typically occur when objects have already penetrated the inner solar system, leaving limited time for coordinating follow-up observations. Earlier detection means more complete monitoring from arrival through departure, capturing activity evolution across the full range of solar distances. Chemical diversity will emerge from large sample statistics. Instead of speculating based on 3 examples, astronomers will compile compositional catalogues, revealing how interstellar object chemistry varies across populations. Some visitors might show carbon dioxide enrichment, like 3I Atlas, while others display different volatile signatures. The patterns will illuminate formation conditions in stellar systems throughout the galaxy. Orbital characteristics from large samples will test theories about ejection mechanisms and galactic dynamics. Inclination distributions, velocity dispersions, and trajectory patterns contain information about how material gets scattered from stellar systems and how it propagates through interstellar space. Current theories make predictions that remain untested due to insufficient sample sizes. The Rubin era will also improve real-time response capabilities. Automated detection systems will flag interesting visitors within hours of first observation, triggering rapid response protocols that direct space-based telescopes and ground-based facilities toward high-priority targets. The coordination demonstrated during 3 iAtlas campaigns will become routine rather than exceptional. Perhaps most importantly, large samples will reveal whether 3 iAtlas's unusual characteristics represent common features of massive interstellar objects or genuinely unique properties that demand special explanation. The mass paradox, chemical anomalies, and morphological peculiarities might prove typical for objects in this size range, or they might remain isolated mysteries requiring targeted investigation. Within 10 years, the statistical foundation for understanding interstellar visitors will transform from 3 examples to hundreds or thousands. That transition will answer current debates definitively through the weight of accumulated evidence rather than continued speculation based on insufficient data. The Vera Rubin Observatory represents a quantum leap in humanity's ability to detect and study transient phenomena throughout the solar system and beyond. When fully operational, this facility will scan the entire southern sky every few nights for 10 years, potentially discovering hundreds or thousands of interstellar objects and transforming the field from anecdote-based speculation into robust statistical science. The Legacy Survey of Space and Time, Rubin's primary mission, will capture images of unprecedented depth across enormous sky areas. The combination of wide field coverage and sensitivity means objects like 3 iAtlas will no longer represent rare surprises, but regular discoveries that accumulate into meaningful population samples. Within a decade, astronomers will have enough data to answer questions that currently remain pure speculation. If 3 iAtlas represents typical interstellar visitor mass, Rubin should detect similar giants regularly. Discovery rates might reach dozens per year for objects in this size range passing through the inner solar system. The statistical sample will quickly reveal whether massive visitors are common or whether 3 iAtlas truly represents an extreme outlier that happened to arrive during humanity's initial surveys. Conversely, if Rubin discovers primarily smaller interstellar objects, the mass distribution will shift back toward conventional expectations. 3 iAtlas would be revealed as a statistical fluke, a tail-end specimen from a population that actually follows predicted size distributions. The accumulating data would restore confidence in ejection models and population synthesis frameworks that currently struggle to accommodate such massive early discoveries. The survey will also detect interstellar visitors at much greater distances from the Sun, providing warning time for detailed observation campaigns. Current discoveries typically occur when objects have already penetrated the inner solar system, leaving limited time for coordinating follow-up observations. Earlier detection means more complete monitoring from arrival through departure, capturing activity evolution across the full range of solar distances. Chemical diversity will emerge from large sample statistics. Instead of speculating based on 3 examples, astronomers will compile compositional catalogues revealing how interstellar object chemistry varies across populations. Some visitors might show carbon dioxide enrichment, like 3 iAtlas, while others display different volatile signatures. The patterns will illuminate formation conditions in stellar systems throughout the galaxy. Orbital characteristics from large samples will test theories about ejection mechanisms and galactic dynamics. Inclination distributions, velocity dispersions, and trajectory patterns contain information about how material gets scattered from stellar systems and how it propagates through interstellar space. Current theories make predictions that remain untested due to insufficient sample sizes. The Rubin era will also improve real-time response capabilities. Automated detection systems will flag interesting visitors within hours of first observation, triggering rapid response protocols that direct space-based telescopes and ground-based facilities toward high-priority targets. The coordination demonstrated during 3 iAtlas campaigns will become routine rather than exceptional. Perhaps most importantly, large samples will reveal whether 3 iAtlas's unusual characteristics represent common features of massive interstellar objects or genuinely unique properties that demand special explanation. The mass paradox, chemical anomalies, and morphological peculiarities might prove typical for objects in this size range, or they might remain isolated mysteries requiring targeted investigation. Within 10 years, the statistical foundation for understanding interstellar visitors will transform from 3 examples to hundreds or thousands. That transition will answer current debates definitively through the weight of accumulated evidence. Every interstellar visitor carries information encoded in its physical structure, chemical composition, and dynamical properties. These wandering messengers reveal conditions in stellar environments we can never visit directly, providing samples of matter shaped by alien suns billions of kilometers distant and billions of years in the past. 3. iAtlas represents a cosmic archive, a frozen record of processes operating in stellar nurseries fundamentally different from our own. The carbon dioxide enrichment detected by JWST tells a story of formation in the frigid outer reaches of its parent system. Temperatures below -125 degrees Celsius are required for carbon dioxide to condense as solid ice in significant quantities. This chemistry points toward birth beyond what astronomers call the carbon dioxide snowline, in regions so cold and distant that sunlight barely registers as warmth. Most objects in our solar system formed closer to the sun, where water ice dominates volatile compositions. The outer solar system contains carbon dioxide, but typically as a minor component mixed with water and other ices. 3. iAtlas's chemistry suggests a different environment where carbon dioxide became a major constituent, implying formation conditions more extreme than anything locally familiar. The nickel emissions without corresponding iron signatures might indicate unusual metal chemistry in the parent protoplanetary disk. Different stellar systems produce different elemental abundance patterns based on the nuclear processes that created their parent stars. A system enriched in specific heavy elements through nearby supernova contributions could produce debris with chemical fingerprints that deviate from solar system norms. These chemical signatures provide glimpses into stellar nucleosynthesis and galactic chemical evolution operating across vast scales. Every stellar system represents a unique chemical experiment, processing primordial hydrogen and helium through nuclear fusion to create heavier elements. The products get distributed through stellar winds and supernova explosions, mixing into the interstellar medium where they seed formation of subsequent stellar generations. 3 iAtlas samples this chemical diversity directly. Its matter formed from interstellar material enriched by previous stellar generations in a different region of the galaxy. The isotopic ratios, elemental abundances, and molecular compositions all carry information about the chemical history of matter cycling through stellar life cycles over billions of years. The size and mass of 3I Atlas might reveal information about planetary system architecture in its birth environment. Objects this large typically form in massive protoplanetary disks with sufficient material to build substantial solid bodies. The ejection required to launch such a massive specimen into interstellar space implies powerful gravitational interactions, possibly involving multiple giant planets or close stellar encounters during clustered formation phases. Understanding the interstellar medium through direct sampling transforms it from an abstract theoretical construct into a tangible environment filled with debris carrying specific histories. Each visitor provides another data point, another sample from the vast reservoir of matter drifting between stars. The accumulated information illuminates how stellar systems form, evolve, exchange material, and contribute to the cosmic ecosystem. 3I Atlas is more than an object passing through our solar system. It's a messenger from the galactic medium, carrying news about conditions and processes operating throughout the vast spaces that separate stellar systems. Reading that message requires decoding the physical and chemical information preserved in its structure, a task that pushes observational capabilities to their limits, but promises insights into environments beyond direct reach. A fundamental question haunts the 3I Atlas discovery. Have we finally achieved the technological sensitivity to see what was always there? Or are we witnessing genuine statistical anomalies in visitor characteristics that demand explanation beyond simple detection bias? The answer matters profoundly for interpreting what this object represents. Survey capabilities have improved dramatically over the past decade. Wide-field telescopes like ATLAS, PAN, STARS, and Catalina Sky Survey now scan enormous sky areas repeatedly, building databases of moving objects that automated software flags for human attention. The combination of aperture size, detector sensitivity, and sky coverage has crossed critical thresholds that make routine interstellar object detection possible for the first time in human history. Before these facilities came online, interstellar visitors could have passed through the inner solar system undetected countless times. They move quickly, remain visible for limited periods, and require specific observation strategies to distinguish from the far more numerous population of solar system asteroids and comets. The detection infrastructure simply wasn't capable of systematic discovery until very recently. This timing raises an uncomfortable possibility. Perhaps massive interstellar visitors have always been passing through at current rates, and humanity only now possesses instruments sensitive enough to detect them. The apparent anomaly of finding a giant object third might reflect detection thresholds rather than genuine population statistics. We see what our technology allows us to see, and threshold effects can create misleading impressions about underlying distributions. Brightness plays a crucial role in detection probability. Larger objects reflect more sunlight and develop more prominent comas when active, making them easier to spot at greater distances. A 5-kilometer nucleus like 3I Atlas should be detectable farther from the Sun than a 500-meter object, providing longer observation windows and higher discovery probabilities, despite being intrinsically rarer. The ecliptic alignment contributes additional detection bias. Survey telescopes focus efforts on regions where most solar system objects reside, the band of sky close to the planetary plane. Objects like 3I Atlas approaching near the ecliptic benefit from optimal survey coverage. Visitors with highly inclined orbits might pass through under sampled sky regions, reducing discovery probability regardless of intrinsic size or brightness. Activity levels create another selection effect. 3. I-Atlas's vigorous outgassing makes it more detectable than an inactive object of similar size. The extended coma increases apparent size and brightness, helping it stand out against background stars. Dormant interstellar visitors might pass unnoticed even if they outnumber active specimens, biasing discoveries toward objects that happen to be sublimating during solar system passage. Distinguishing between detection threshold effects and genuine population anomalies requires larger sample sizes that span the full range of object properties. Until Vera Rubin Observatory begins flooding discovery lists with interstellar visitors detected at various distances, inclinations, and activity levels, the threshold question remains open. We might be seeing a biased sample that tells us more about our telescopes than about the interstellar medium. Or we might be witnessing the early hints of a population distribution that violates theoretical expectations in ways that demand explanation. Only time and better statistics will reveal which interpretation proves correct. For now, the detection threshold question adds another layer of uncertainty to an already complex puzzle. 3. I-Atlas has already taught us crucial lessons, regardless of how its mysteries ultimately resolve. The object forced astronomers to confront gaps in theoretical understanding, pushed observational techniques to their limits, and demonstrated that the universe still holds surprises even in domains we thought we comprehended. These lessons transcend any specific explanation for its unusual properties. The mass paradox revealed how little we understand about the full range of behaviors possible in cometary physics. A century of studying solar system comets created confidence that outgassing dynamics were well mapped. 3. I-Atlas shattered that confidence by displaying activity without expected acceleration, occupying parameter space that theoretical models claimed should be empty. The disconnect between observation and prediction highlights how unexplored regimes can hide in plain sight. The chemical anomalies demonstrated that formation conditions vary more dramatically across stellar systems than models predicted. Carbon dioxide enrichment, nickel without iron, and other compositional oddities challenge assumptions built on solar system experience. Each visiting object samples a different chemical environment, revealing diversity in planetary formation processes operating throughout the galaxy. The population statistics nightmare exposed how insufficient data can mislead statistical inference. With only 3 confirmed interstellar visitors, drawing conclusions about typical characteristics becomes meaningless. Early samples often include outliers that vanish into broader distributions as sample sizes grow. 3. I-Atlas might represent genuine anomaly or simple statistical fluctuation, and current data cannot distinguish between possibilities. The observation campaigns showcased modern astronomy's collaborative power. 4,000 measurements from 227 observatories transformed Earth into a planet-sized telescope. Space-based assets provided complementary data from perspectives impossible for ground facilities. The coordination will serve as template for future campaigns studying transient phenomena across the solar system. Most importantly, 3 I-Atlas reminded us that discovery remains possible in an age often characterized by incremental progress. The object arrived unannounced, violated expectations, and generated genuine scientific puzzles that lack obvious solutions. This capacity for surprise represents one of astronomy's most precious qualities, the promise that nature still conceals secrets waiting for revelation. Whether 3I Atlas proves to be a massive natural comet, a planet formation seed, or something even more extraordinary, it has already succeeded in forcing deeper thinking about processes operating between stars. The questions it raised will drive research for years, regardless of how they ultimately resolve. The silent giant's message is clear. The universe remains stranger and more complex than our theories predict, and the space between stars holds secrets we're only beginning to glimpse. 3I Atlas continues its journey outward, moving back toward the interstellar depths from which it came. Telescopes around the world remain trained on the silent giant as it fades slowly from view, collecting data that will be analyzed for years after the object itself becomes too faint to observe. The watching continues even as the visitor departs. The questions it raised persist long after perihelion passage. Is it truly as massive as preliminary estimates suggest, or will refined analysis bring the numbers back toward conventional expectations? Do the chemical anomalies represent genuine exotica, or simply unfamiliar applications of familiar physics? Will population statistics from future surveys reveal 3I Atlas as typical or extraordinary? These answers will come gradually through continued observation and theoretical refinement. The next interstellar visitor might arrive within months, or it might take years. The Vera Rubin Observatory will eventually flood discovery lists with dozens of new detections annually, transforming speculation into statistical science. But until then, 3I Atlas stands alone as the most recent messenger from the space between stars. Whatever it is, wherever it formed, this object has already changed how astronomers think about interstellar debris. It demonstrated that visitors can violate expectations in fundamental ways. It showed that sample sizes of 3 provide essentially zero statistical power for understanding populations. It proved that the universe retains capacity for genuine surprise, even in seemingly well-understood domains. The techniques developed to study 3I Atlas, the observation protocols, the international coordination, the rapid response capabilities, all these will serve future campaigns when the next enigmatic visitor arrives. And it will arrive. The galaxy ensures a steady stream of debris wandering between stellar systems. Humanity has finally achieved the capability to detect these wanderers systematically. 3I Atlas may fade from the telescopic view, but its legacy will shape interstellar object astronomy for decades. The silent giant taught us to watch more carefully, question more deeply, and remain open to possibilities that challenge comfortable assumptions. The next visitor might be even stranger. Now we're ready.